Okay, so I am continuing to work on my electric field due to parallel plates. And in the previous video, what I did was I started off with the electric field due to a ring of charge along the axis of a ring. And then I did the electric field due to a ring, and I did a numerical calculation by breaking into a finite number of points. After that, I did an analytical calculation for the electric field due to a disk, by breaking into a bunch of rings. But only on the z-axis. And then finally I created like 20,000 random points to represent charges on the disk and calculate electric field due to that. So I want to do now two disks, right? So if I have a positive charge disk and a negative charge disk, what's the electric field in the center? I'm going to do that two ways. I'm going to use an approximation for the electric field along the z-axis. And I showed with the numerical version that it's fairly constant if you're close to the disk. I mean, if you don't have to be on the z-axis. You can still get an approximation for the electric field. And then I'll do it numerically with a Monte Carlo calculation where I create 20,000 random points. Okay, so let's get over here to this. Let me turn off this camera so that we have more room. Camera off. Okay. So here I have two parallel plates, a charge plus q and a minus q. They have the same radius, r, and they're separated by some distance, s. Now, this is the exact model for the electric field due to a disk on the axis of the z-axis. If z, though, where z is the distance, so if I can draw it like this. Here's my one plate. There's my plate on the xy plane, and that's z. And then, so if I have, this is my z value, but if I'm really close to this, and this is r, if z is very, very close to the disk, such that z is small compared to r, then up here, I get r squared plus z squared is really just r squared. Then I take that to the 1/2 power, and I get z over r. So this is my approximate value for the electric field due to a disk if I'm close, and I'm going to use this. So now let's say that I have two disks. I'm going to put this one right here, like that. And so this is a plus q, and this is minus q. So if I'm right here, let's just even put it on the z-axis. And this is a terrible picture because it really should be a lot closer. So I have two electric fields. This one's going to make an electric field going this way, and we'll call that E plus in the z direction. This one's also going to make an electric field going that way. I'll call that E minus in the direction, right? Because the charges are going to be going that way. So I can find the total electric field using this twice. So let's just say E plus, let's write that as E plus in the z direction is going to be equal to Q over 2A epsilon naught 1 minus Z over R. E minus is going to be equal to, okay, so this is a distance S. And so this is the distance I need right here. So this is the distance, this is going to be S minus Z. So I get Q over 2A epsilon naught 1 minus, not Z, but S minus Z over R. I'm just trying to make sure that that's, yeah, so S is a positive number, so this would be positive, and this will give a value also in the X direction, the Z direction, because it's still in the same direction. So now I can find my total electric field. It's going to be the sum of these two. So EZ, this is minus. EZ is going to be this stuff, so Q over 2A epsilon naught. Now I'm going to get 1 plus 1 is 2. And then I'm going to get this term, so let's put minus Z over R, and then I'm going to get this. Let's write this as minus S over R, and then plus Z over R. And you'll notice that these terms cancel. So I get the two, I can, yeah, let's factor that out, I guess. So I get 2Q over 2A epsilon naught 1 minus S over 2R. But the important thing here is that this is a constant value. So it's constant. Okay. And if S is really small compared to the radius, then this is just, that goes away. So I get approximately equal to Q over A epsilon naught as the electric field in the Z direction. And that's the electric field that we want to find. Like that. Equals. Okay. So now let's do this numerically. I'm going to use my code from before so I don't have to rebuild that. And all I need to do is, so I have here my parallel plate of 1,000 points. I've already got this. And I can find the electric field anywhere. All I need to do is add another plate right here with another 1,000, 10,000, 2,000, whatever, how many points, and then calculate the electric field. Now, I can't have this all as one big list because these are going to be positively charged and these are going to be negatively charged. But let's just switch over to Python and let's see if we can make this thing work. I'm doing this live, so I might make some mistakes. Okay. Okay, so here is the program I had before. Let me turn off the camera. And so there's my plate. It's in, let's rerun this. It actually takes a while to run. I'd like to keep it just like this because this already has a whole bunch of electric fields too, right there in the middle. And so I just have a whole bunch of values, locations where I calculate the electric field, and all I need to do is add a plate over here. Okay, so let's add the disk first. The disk, I'm going to go, this is make sure that works fine. Let's just do this piece by piece. So I'm going to say Q disk 2 is cylinder. The position is going to be equal, I need S. Let's say S equals, how far apart? Let's see, the radius of the disk is R, which is 0.05. So let's say S equals, let's put it at 0.01 centimeter, because if I put it too close, it's going to be hard to see. So this is going to be a position of vector 0, 0, S. Axis is the same, vector 0, 0, 0.002, and then the radius equals R. I should probably make it a different color, but I'll just leave it. Let's just run that and see what that looks like. Okay. So there's my two plates. And so the vectors extend through there. That's a little weird. Let's make it a little bit further apart, and we can always change it later. Okay. So now I need to, this part right here, this lines 14 through 18, make an electric, a whole bunch of points for the positive plate. So now we need to do the same thing for the negative plate. And so I'm going to copy this. And I do need a QS2. Let's call it QS2 equals an empty list. And N equals 0 again. I need to start over. Now, I'm making a vector in the XY plane still, but the Z component is going to be equal to S. Right? So it's still generating the X and Y coordinates are random numbers, but that's fine. And now here, I can't do this. I can't do if mag of the R is less than or equal to R, because I have to do this. I have to say it's in the XY plane. So I'm going to say square root of R temp dot X squared plus R temp dot Y squared. And so that excludes that Z component, which I don't want to be in part of. I'm generating these XY values and they have to be in the circle. And if I use the other one, it would make it really weird. Now this needs to be QS2, QS2, but I think that works. And let's go up here. I had N as 10,000. Okay, let's keep it like that. Okay, let's just do it all in one swoop. I may have to change the value, the magnitude of my vectors, the scale. I know I'm going to have to because it's going to be bigger. So let's just do that. Yeah, before I forget, E scale, let's say it's 10 to the negative, let's say it's half of that. So let's say 1 times 10 to the negative 7th. Let's just try that. Now up here, I go and calculate, let's call this E plus, EP for E plus. That's the electric field due to the, well, I could do that with two things. That's fine. No, I don't have to do that. I just leave it as E. Now I just need to go through, that goes through all the positive charges and calculates electric field. Now I just need to do the same thing for the negative charges. So I can say for RQN in QS2, it's the same thing. Let's copy this. Why copy? Why type it when you can copy? And, oh, what did I do? Okay, I can delete that. So then I can calculate my R value, that's fine. Changes to RQN. I think I could leave it as RQ, but DE is going to be K, it's going to be negative, right? Because those are negative charges. But other than that, everything's the same. And everything's the same here too. So I think that works. I think it does. R2. Let's go. Okay, let's save it. Oh, I should have copied this. Okay. I didn't do that. Let's just copy everything and go to make a new one. And call it parallel plates. I don't want to edit, I don't want to ruin my old code. And I may have done that already. So, ooh, where'd it go? Okay, I just did a new one. Okay, let's get rid of that. Okay, I may have really messed up things. Save it and run it. Okay, so, weird. Maybe my E is too, are those, do we just not have electric fields? Maybe make this bigger. Maybe they're just too small. Oh, I had it at, oh yeah, I had it at 5 times 10 to the negative 6. So let's do this at, 1 times 10 to the negative 6. Yeah, I made it that way too small. There we go. Goodness, look at that. That's pretty cool. Okay, now let's do the following. Let's print the value. Let's print E. I should have done that, but let's print that out. So let's go down here. What the heck? Delete that. Now I want to print the value. That's the last value of E. That's fine. Okay, so there you see the Z component is 5,546. That's important. There is a, oh, that's the last electric field. So that one is over here. So it does have some other component. What I want to show is let's just do one single point for the electric field over here on the outside. Because the key thing is if I have these two plates, there's a strong electric field on the inside, but a weak electric field on the outside. So let's do this. Let's calculate that a couple more times. Let's find that in the center. So let's say E center equals vector 0, 0, 0. And then E out equals vector 0, 0, 0. And then I need two positions. So R center equals, it's going to be vector 0, 0, S over 2. Right? That's right there in the middle of those two plates. And then R out is going to be equal to vector, let's say 0, 0. So the distance between them would be S. So if I go a little bit further, let's go, let's say 3 times S over 2. Yeah. So now I need to calculate those. So I'm going to need to do this whole stuff over again. Right here. This. I'm just going to print it. I'm not going to display it. So for RQ, that's fine. And I'm going to change this to E center. And then I'm going to change this to R center. And then I'm going to do this down here, R center, and then E center. And then print that one, print E center equals E, and the units will be volts per meter. And then I'm going to do the same thing for the out. So now I'm going to say change this to R out. Out. That's fine. Out. Out. And this is going to be out. And then this is going to be out. Ooh, I messed up. Out. So this up here should be E center too. Okay, and then I'll need to print that. Print, oops. Parent E out equals E out. I messed up again. I see where I messed up. Good thing I'm typing stuff. Volts per meter. And this should be E center up here. Okay, let's see if this sucker works. Save. Run it. Oh man, I should have done something else. Did I get an error? End in line 57. Oh, these are indented too much. Oh, that's fine. That needs to be dedented. Dedented. Okay, now let's do one other thing. Let's print out the theoretical calculation. So did I already calculate A? No. Okay, so the area of the disk, A, is going to be equal to pi times r squared. I do have epsilon naught, EPO. Didn't I? Well, I did it over here. EPO. Let's just copy that. I'm too lazy to do that. Parallel plates. EPO. Okay. That's epsilon naught. So now let's print out the theoretical calculation. So E theory in the middle equals, I'm just using my formula over here. Where'd I put it? I had Q divided by A times EPO. Print E theory, and you got to spell it right. You don't actually have to, but E theory volt per meter. Okay, now let's run this thing. I should save it and run it. Okay, so E center is, I have, check that out. Oh, it's not quite the same, right? But these two, the X and Y components are very small, but they're not actually small because of random fluctuations in where those data points actually are. And you notice though, but it's pretty close to the value, the theoretical value. I think if I increase the number of data points up to, let's say, 20,000 or rerun it, it should get closer. I'm pretty happy with that. But then E outside, you'll notice that it is much smaller. Okay, it's much smaller because now the two electric fields are acting in opposite directions as you get outside the plates. So they will cancel some, but not perfectly. Okay, so I think there's a whole bunch of cool things you could do with this, play around with fringe effects and stuff like that, but I'm going to stop this right here, leave this with you. I'm going to leave you the code. I'm going to leave you all the other things. I think I'm pretty much done with my electric field due to parallel plates. I do want to do some Gauss's law stuff, but that'll be in the future. So that's it. Talk to you guys later.